Hi, hello. Welcome back. We're going to do another physics workshop. Today we're going to be talking about rotational inertia. Rotational inertia. This is workshop number 7, meant to correspond with your physics series. You've probably looked at rotational inertia a little bit. I often find students coming in, this is a bit of a confusing topic, but if we power through and we get the fundamentals down, I think we'll find that we can understand it pretty solidly, and we won't be looking at too much of what makes rotational inertia complex, which is the calculation involved in what the rotational inertia for a specific object of a specific shape actually is. That's going to involve calculus. For the most part, in these problems at this level, we're going to be telling you a certain value for the rotational inertia, or we're going to be asking you just to solve for it numerically. So you won't have to worry too much about the calculus. It's going to be pretty straightforward algebra in the problems that we're working on today. But before we get started, what's important is just to make sure we have a clear understanding of the core equations that are going to be important for us to do. So you guys remember, you've done for a good bit of time, you've done your Newton's second law, F equals ma. F equals ma. We've used this dozens of times now. What we're going to do today is we're going to work from a similar equation, which is an analog, but it is the rotational equivalent. So if we're looking at F equals ma as a linear motion, then we can consider also a rotational motion or a motion about an axis. And the relevant equation, as we're looking at a force over a distance, and we're looking at an object rotating about a fixed axis, is that the torque tau is equal to I alpha. Tau equals I alpha. You may have seen this before, but let's take a second and really sit with it. So in this equation, we can map the analogs to what is similar to what you've experienced before. So in this, a torque acts like a force, and indeed a torque is composed partially of a force. It's a force that acts over a distance, right? So torque is similar to force in this equation. Alpha is angular acceleration. And we learned in a previous workshop, and you've seen in your physics class, how acceleration and angular acceleration are related, right? Very similar. So this is the analog, the angular acceleration and the acceleration. The angular acceleration has units, you will recall, of radians per second squared versus the uniform or linear acceleration is just going to be in terms of meters per second squared. Okay, and we can translate between those, and we may do that in a problem, but it's just important to see how they're related. So that just leaves us with m and with I. So m is the mass of an object, and you've seen how m sort of represents an object's resistance to being accelerated, an object's resistance to having its velocity changed. If m is very great, if m is large, we have a lot of mass, it takes a pretty substantial force to accelerate the object. Or if we give a certain amount of force, let's say we apply a 10 Newton force to a large mass, we would expect the acceleration to be small. It's hard. It takes a lot of force to move and change the velocity of big objects, and you've experienced that in your everyday life. It's more difficult to change the velocity of, say, a very large dresser, maybe this is a dresser, versus a small crate. And if this is coming at you, if this is falling towards you, say, it's got some velocity, and you're going to need a lot of force to change that velocity, to accelerate it, to bring it to a stop. Or if you want to move, it's moving day, you're moving to a new house, and you want to pick up and move this dresser. Its velocity is 0. You want to change that velocity. You want to get it moving so you can carry it down the stairs or carry it into the moving truck. Well, it's going to take you a pretty substantial amount of force and ultimately a good amount of energy, because you're going to have to apply that force over a distance to move this guy. This smaller crate will be easier because its mass is lower. It's more easy to change its acceleration. And the reason is because it has a lower inertia. So that's another term, we use it pretty interchangeably. Inertia is the concept of how difficult or how easy something is to kind of move around. Specifically, when I say move around, I mean change its velocity. Because you'll remember from Newton's laws that an object in motion wants to remain in motion, and an object that is just staying in place wants to remain staying in place. And it's only when they're acted on by unbalanced forces that they experience an acceleration A and their velocity changes V. Okay, and if any of that was confusing, I would say go back and think it through and get very comfortable with that, get cozy with that, get intimately familiar. And then once it makes sense and you've kind of convinced yourself with some examples, let's look at the rotational analog. Let's look at the rotational analog. And we're just thinking of the concept a little bit before we get to any of the problems. So we're rotating now. I want you to imagine the first problem is for a merry-go-round. So let's go ahead and start thinking about merry-go-rounds. So this is our depiction. This is a merry-go-round from the top, say. Do it in a nice rainbow. I love it. Okay, we're going to put a center dot right there. So this is the central axis, and we're looking at the merry-go-round from above. We're looking for the merry-go-round from above. So it would spin around like this. Okay. So now, if we put a force onto one side of the merry-go-round, well, the merry-go-round doesn't translate, right? It doesn't just start sliding across the ground because it's pinned to the ground. It's pinned to the ground by this central axis right here, and it can rotate about that axis freely with negligible resistance, but it's not free to be translated. It's not free to move through space except in rotation. So if we put a force on the merry-go-round, we have to do this force from a distance. We're doing it some distance from the central axis. This is getting a little cloudy. Let me do it the other side. So let's say we push on the edge here, right? Then you've seen how this is a torque. We're doing a force from a distance. We can only move about this axis of rotation. So we have to consider the lever arm here. We have to consider the force over the distance. That's a torque. And the torque, you may recall, the torque is equal to, you may have seen vector notation, you may see F cross R, where both of these are vectors, kind of as I've drawn them. Or you may have seen FR. If we just take the magnitude of F, the magnitude of R, and we take FR sine theta, where theta is the angle between two vectors. This is equivalent to taking the cross product. Either one of these will give us the torque. Either one of these will give us the torque. And the torque is kind of acting as our force in this analog, this F equals ma analog. And the acceleration, you already saw how that was linked. The acceleration is in meters per second squared. The angular acceleration is in radians per second squared. And instead of being a measure of how many meters something travels, I'm sorry, not how many meters something travels, but how many meters, by how many meters something's speed is increasing per second. So how its velocity is changing as a function of time. The same thing is true for our angular acceleration, but instead of measuring in meters, we're measuring in radians. We're measuring in radians. There's a measure of an angle as we go around the circle. So we're asking really, how much angle do I turn per second? By how much is my velocity, my angular velocity, increasing or decreasing? How does it change? That's what we're answering with the angular acceleration. So the final piece, and the main kind of focus for today is this I. So I've already talked about or touched on a little bit how somehow mass is an analog for this quantity I. And let's talk about what this I is. Sometimes you'll hear it called the moment of inertia. I think that's a bit of an older term. I don't hear it as much anymore. I don't like it as much either. A better term, I think, is rotational inertia. That's really what we're talking about. We're talking about the rotational resistance to a change in its velocity. Remember I said how just as mass and inertia are interrelated, the more mass something has, the more inertia something has, the more difficult it becomes to change its velocity. Let me just write this in letters instead of my bad handwriting. How about that? So we're talking about the rotational inertia. That's I. Capital I. Okay. So we're familiar now with all of these quantities, and I think we're ready to, let me give us some examples. Let's make it more concrete, this idea. So this may be common to your physical experience. If not, I encourage you to take some physical things and go out and play with it a little bit and try it. So we're thinking about how can we change something's rotational inertia? How do we change the degree to which it resists having its velocity changed, right? Which would correspond to a change in speed, a change in the direction that it's rotating, all of those things. So let's think about the merry-go-round. I think it's pretty good. Let's imagine a big, large, heavy merry-go-round. You can kind of get an intuitive sense. You imagine if you were trying to start that thing up, it would take a good bit of force, and you wouldn't just touch it and it would just go flying, spinning at high speed, right? No, it's got a lot of mass. It's kind of heavy, you would feel. And so you would have to put a good amount of force, and you would kind of you would expect a slower acceleration. Since the mass is large, the rotational inertia is also large. But rotational inertia is more complex than just mass. It involves the mass, but it also involves the distance from the rotating axis. You can see this. The common example is usually given as the figure skater. You've seen maybe a figure skater in the Olympics. The figure skater will begin a spin with their arms kind of spread out. They've got their mass spread over a distance, and they're spinning up in this direction. And then when they're ready, they'll tuck their arms in tight. They'll tuck their arms tight to their body. And what you'll see is that they begin to spin faster. They begin to spin faster. The reason is they've reduced their rotational inertia by tucking the mass tighter to themselves. So when the mass is less spread out, when it's less distance from the rotating axis, we can reduce the rotational inertia. And you can try this out if you want to just pause and go ahead and stand up and start spinning around in your room. You'll notice a big difference between when you're spinning around with your hands out and when you spin around tucking your arms tight to yourself. And this is true for things that roll and things that rotate in general. The tighter the mass is packed, the easier it is to get them spinning. And you can test that out. Try to develop a good intuition for it, just like we did with F equals ma. Get comfortable with it, get cozy with it. And then when you are, we can tackle these problems. And I think they won't be too confusing once that's done. Now, I told you that it depended on the mass. I told you that the rotational inertia depended on the mass. And I told you it depended on the distance. But how does it depend on those things specifically? Is it directly proportional? Is it something else? So for a point mass, and we're not talking about continuous distributions of mass yet. I told you that would involve calculus. So don't worry about that just yet. So the moment of inertia, or the rotational inertia, is going to be the sum of element of mass, 1 point mass, say, multiplied by the distance at which the distance from the axis of rotation to that point mass squared. And then we sum up all the different point masses. We sum up all the different point masses. So let's look at our figure skater and calculate what that would be. We're spinning on our central axis, right? We can imagine it being right at the center of our head or right at the center of our body, kind of down the spine. And then we could consider this point masses. Let's consider what it would look like if you're holding heavy weights in each hand. You have a 10-pound weight in each hand. What would be the rotational inertia from this setup? Well, let's make it a little simple on ourselves, because I told you we didn't want to use calculus. So let's not think about the mass that's distributed over your arm. Let's say that that's negligible. Let's say that that's small enough that you don't have to worry about it. My arms aren't particularly large. This wouldn't be a horrible approximation for me. So we've got two weights on the end here, and we have got several different masses that we need to look at. So here's some mass. This is the mass of our body, right? And then so this will be M1. And then here's another mass. This is the mass of the weight. This is going to be M2. And then here's another mass. This is the mass 3. All right. And this is the 10-pound weight as well. And they're all a distance. And let's say, how long are my arms? We'll keep it easy. We're just doing a little practice here. Let's call that a meter, 1 meter. Or I tell you what, my arms are not 1.5 meters long, but let's say 1.5 meters, 1.5 meters. That way, just so when we square them, something happens and you guys can see that. So my drawing is getting a little messy, but we're going to say that R1 and R2 are both 1.5. R1, that's my left arm, let's say, is equal to 1.5 meters. It'd be kind of crazy if I had 1.5 meter long arm. R2 is equal to 1.5 meters as well. Let's say M1, which you remember was my mass. Let's say M1 is, my mass is about 65 kilograms. 65 kilograms. All right. And then we also have some additional mass. We've got mass 2 is equal to, I said 10 pounds, but let's make it 10 kilograms. I'm not trying to make you guys do some conversions. And let's do M3 is also going to be equal to 10 kilograms. Okay, so can you tell me what is the rotational inertia of this setup while my arms are extended? Based on what I've told you so far. And remember, you can ignore the mass of my arms. We can just treat my whole body as essentially being a point mass centered on this central axis. Some simplifying assumptions, but this is pretty on par for the problems that you'll be handling, at least initially. So let's do that. So there is no R3, right? There's no R that's associated with the central mass. So that is just going to be 0. There's 0. So if we sum this up, we can go M1, and you know what I should do? Sorry, this is kind of tricky notation. I don't want to fool you guys. Where's my eraser? I call this R1 and R2. Let's call it R2 and R3 so that it corresponds to the masses. Okay. So we're going to say M1, and then we're going to multiply M1 by its distance from the central axis, which is 0, right? Which is 0. All right. And then we're going to add on to that because we're doing the sum, right? So MI, now I do M2, so mass number 2. Okay. Mass number 2 times R number 2, which is 1.5. And I'm going to square that. And then we're going to add the sum. This is going to be mass number 3. And that's going to be R3, it's 1.5. We're going to square that. Okay, so we punch this in. You can punch it in quickly to your calculator. Let's see. So we have Since my mass over here is just going to cancel out, we're treating it as just being a point mass at the center. We've got 10 times 1.5 squared times 2 plus, or in other words, plus 10 times 1.5 squared. Okay, so I get our rotational inertia. And what should be the units here? What should be the units here? We had kilograms, right? Kilograms for my mass. And then we had meters squared. So kilogram meters squared, and 45 would be I here. And we did that same calculation, but we tucked the mass in tight, right? We lower this radius. You can see how that rotational inertia decreases. We'll develop some more intuition about this. Just my brief explanation. Now we're going to go ahead and launch into problem 1. Okay, so we said consider the father pushing a playground merry-go-round. He exerts a force of 250 newtons at the edge of the 50-kilogram merry-go-round. It has a 1.5 meter radius. Calculate the angular acceleration produced. That's part A. First, when no one is on the merry-go-round. So let's do that. So let's first just do some underlining here. So it tells us a force. It tells us 250 newtons. It tells us, it looks like, at the edge of the merry-go-round. There's a 50-kilogram merry-go-round. It tells us the mass has a 1.50 meter radius. It tells us R. And it says calculate the angular acceleration. So it's asking us in this problem, it's asking us to find A. And in order to do this, if you're looking at your torque here, so we have the information. Well, let me be explicit. Let me show it out. So here we've got F. If you feel confident to tackle this problem, go ahead and tackle it. Just jump straight into it. You will have to look up a figure, which is the rotational inertia for a disk. I want to ask you to calculate that. You'll be provided with a table, or that will be a value that you can look up. So we have a 250 Newton force. We have M equal to 50 kilograms. Okay. We have R is equal to 1.5 meters. Is that right? Yes, it was 1.50 meters. Okay. So let me call this big R because it's going to be the radius of the whole merry-go-round. That's just what I think. Okay, we're not curious about this child yet. We first just want to look at when no one is on the merry-go-round. Okay, so we have our core equation. The equation that is going to relate to the angular acceleration. And it says the torque is equal to I alpha. Torque equals I alpha. So what do we want? It says, what is the angular acceleration? We want to solve for alpha. So let's get alpha on its own. The way I'm going to do that is I'm going to just divide both sides by I. So I'm going to have the torque divided by the rotational inertia is going to be equal to the angular acceleration. T over I equals alpha, or tau over I. Now, we have this, but we don't know the torque directly. They didn't just tell us what torque the father puts on it. They told us some information about the force. They basically told us the force. So we're going to have to find the torque somehow, and we're going to have to find I somehow. We have one equation here, right? This is one equation. So if we have one equation, we can solve for, at most, one unknown thing. And we know the unknown thing is this. This is what they're asking us to find. So we need to somehow find out a solution, a numerical value for these two guys, And they did not tell us these straight in the problem. So we need to use our heads a little bit. We need to think about what we can combine, how we can expand, etc., etc. Okay, so let us first do the torque. Let us do the torque. So I showed you guys earlier, we have this right here, that the torque is going to be equal to, see if we can copy that, FR sine theta, FR sine theta. All right. And we have here our merry-go-round. Merry-go-round. That looks round enough. And the father is pushing it. He's pushing. So let's give him the force. So here is our force. This is a force of 250 newtons. 250. 250 Newton force. All right. And that is acting over a distance from the center. And this distance is 1.5 meters. 1.5. Not 0.5. 1.5 meters. There we go. Okay. Now, these are at a right angle, at least the way I have this here. They actually don't specify. He just says he's pushing at the edge of the merry-go-round. They don't say what angle he's pushing at. But I think it's safe to say if you know he's a dad, he probably knows what he's doing, which is that he should push it tangentially, not that he should try to push into the merry-go-round or out from the merry-go-round. Doesn't make any sense. So I think it's safe to assume that this is a 90-degree angle between them. Doesn't explicitly say so, but that's the common sense of it. So we've got a 90-degree angle right here. So the sine of 90 degrees is just 1. So then tau, our torque, is just equal to F times R. F times R times 1. F R. All right, perfect. So we're good there. We're good there. We can replace tau with FR. And now what do we have? We have FR over I. We still need to find this I value. So I value you have for your course somewhere, I'm sure, a table of common rotational inertias that were given to you. If you don't, they're easy to Google. You'll be using these a lot. For the disk, I know that it is 1/4 the mass of the disk times the radius of the disk squared. Actually, I say I know that. I better double check. Don't want to steer you guys wrong. Rotational inertia of solid disk. Yes, 1/4 mr squared. Okay, provided it's rotating in this axis in this way. Okay. Let us see. All right. So this is I. So this is I. So we can turn this into FR over 1/4 mr squared. Now this R that I put, this R from FR sine theta, what is that value? It's 1.5 meters, or it's the value of big R, the full radius. The full radius. So I think we can simplify this a little bit. You guys okay if I put this 4 on top? We're dividing by 1/4 is the same thing as multiplying times 4. So let me put 4F divided by MR. And let's just show. So we've got 4FR, got 1 R on top, 2 R's on bottom. R 1 minus 2. We're going to just be left with 1 R on bottom. And this becomes 4F, 4 times the force, divided by MR. divided by mr. And that's going to equal the acceleration, the angular acceleration of the merry-go-round. So we can punch this into our calculator real quickly. What do we have? So 4 times 250 on top, 4 times 250. We're going to divide that by the mass of the merry-go-round, was 50 kilograms. And 1.5 was the radius. I get an angular acceleration of 1.33 times 10 to the 1 radians per second squared. Okay, and there we go. So there's our answer. Put that in a box. Okay, so here's the acceleration with no child on the merry-go-round, with no child on the merry-go-round. So that's our answer for part A. Part A. Okay. There we go. Now let's start over on part B. So part B complicates the situation a little bit. The difference in part B, what do they add? They say, now what is the angular acceleration produced when there's an 18 kilogram child sitting 1.25 meters away from the center? Okay, so let's draw this again. New scenario. So here's our merry-go-round. We've got our vectors. Here's one from the center. This is the radius right here. Okay. And that is, R is 1.5 meters. 1.5. Yeah. Okay. And then we have that same force is being applied, that 250 Newton force that Dad is giving. So we have 250 Newtons is our force still that the father's giving. We're pushing down this merry-go-round. It's the same as it was before, but there's one difference. And that one difference is now the kid is sitting on the merry-go-round. Probably the whole point of doing the push. Maybe they're sitting a little further towards the edge. They grabbed onto one of the bars. They're about there. Let's go ahead and I'll put them right here. So there we go. All right. So this is our child. Okay. Now the child is sitting 1.25 meters. 1.25 meters from the center. 1.25. So not quite fully out at the edge, but most of the way there. Okay. Let's make sure we got that right. Away from the center. Consider the merry-go-round. A uniform disc with negligible rotating friction. Super. We've done that. All right. Now, let's do our same equation. We're looking for the angular acceleration. And you have your core equation that you always go to straight off the bat. We have that tau is equal to I alpha. Problem about rotational inertia, probably going to use this formula. Tau equals I alpha. And we're looking for alpha, once again. So it's going to once again take the form of alpha is equal to tau over I, rotational inertia. But the question is, what is the rotational inertia now? Because we've changed the mass and we've also changed the mass distribution. So down here, we have that the mass of the merry-go-round is 50 kilograms. All right. And then we also have a child's mass, and the child's mass was 18 kilograms. 18 kilograms. That's right here. Okay. So how are you going to solve this? How are you going to find the rotational inertia? So for the disk, we already found it. We found that it was, let's see, I disk. call this I disk. And it was 1/4 the mass of the merry-go-round, we'll call that big M, times R, big R, the radius of the merry-go-round, squared. But what is the rotational inertia due to the child? We're going to say I child. Okay, so give that a go. Try to figure that one out. Right, so the rotational inertia of a point mass, we're going to treat this child as a point mass, is going to be the sum of the mass times the square of the radius away from the center axis. So for the child, we have how many masses? We're just going to treat the child as one 18-kilogram mass. That's what the problem tells us to do, just giving us the total mass of the child. Okay, and we're going to find the child is placed 1.25 meters away. So all that we really need to do, there's only one thing to sum up, right? There's just one mass. So that mass is 18 kilograms. Let's call that little m for the child. And then the radius, let's call that little r. And we're going to square that. Okay, so now what would be the total rotational inertia? What would be the total rotational inertia? Take a guess. I'm pretty sure you know. We're just going to add these two together. The total rotational inertia is the sum of all the rotational inertias that are acting on this thing to try and keep it from accelerating. So it's just going to be 1/4 m r squared plus little m little r squared. We plug that into our formula. We're basically already almost done. So now instead of I, we want I total. We want the total rotational inertia. We want that to be over tau. We discovered that that was FR. Remember, we found that the angle was 90 degrees. The sine of 90 degrees, or the sine of pi over 2, is equal to 1. So this is F times R times 1, it's FR, divided by, now we're going to put I total, so 1/4 big M, big R squared. Okay, and I have made a little mistake here. See if you catch it. I'm going to finish writing and then I'm going to fix it. My notation is sloppy, sloppy, sloppy. Slap on the wrist. Okay, what is my mistake? We're going to delete this. I put this little r because that was straight from our equation, but little r means something else in this problem. I need to get rid of this. This needs to be a big R because the force is at 1.5 meters away. The force is at 1.5 meters away. The father is pushing from the edge of the merry-go-round, not from the place where the child is on the merry-go-round, but from the edge. This is F, this is big R. Okay, let's plug this in and see what we get. All right. 250 newtons times the radius of 1.5 meters divided by 1/4 times the 50 kilogram merry-go-round times 1.5 squared added to, and this is all underneath. This is all underneath the bar here. The mass of the child, 18 kilograms times 1.25, and we're going to square that. All right, and now prediction before you punch it into your calculator. Will the angular acceleration be greater or will it be less? What do you think? Well, we have increased the rotational inertia. So we expect to find, does it rotate more quickly or does it rotate less quickly? Okay, and we get 6.67, I think I get, times 10 to the 0. We don't need to worry about that. 6.67 radians per second squared. Okay. Okay. All right. And so for our given torque, for our same torque, we had to contend with this different rotational inertia. We were dividing by the rotational inertia to find the angular acceleration that we achieve, and we find it's 6.67 radians per second with the child on. Okay, and that brings us about out of time. We've gone through this problem. Let's see, A and B. Yeah. And this gives you a good sense, I think, of how to tackle some of these rotational inertia problems. We could do these other ways, right? What are the other ways that this could go? We could be solving for the torque. We could be solving for the rotational inertia. Whatever two of these you give me, I can solve for the third. And really, since the torque is broken up into a force over a distance at an angle, I could also try and solve for those pieces. I could try and solve for those pieces. Or since the rotational inertia is composed of, it depends on the mass and the distance from the axis, r squared, I could maybe try and find the radius, or I could maybe try to find the mass, depending on what information you give me, And then remember to connect this idea, the angular acceleration, to your kinematics and to the rotational motion problems that we've solved previously. Sometimes your problems will be a mix of these. So I encourage you to tackle some more of these problems from your workbook, but this is your approach for solving for rotational inertia. I hope you found this useful. I hope it was helpful to you. If you're still confused in the slightest or you want any more extra practice, we're happy to help you at SV25 at the Tutoring Center. Thank you. Have a great day.